Continuing our discussion into Chapter 3, this is the second video in a two-part series in regards to how to summarize numerical data. If data has a distribution that is bell-shaped or symmetrical, we are going to imply the empirical rule to this data, and it can be used to determine the percentage of data that lies within a certain number of standard deviations of the mean. This is often referred to as the 68, 95, 99.7 rule. By definition, what the empirical rule says is that approximately 68% of the data will lie within one standard deviation of the mean. So down here, if I look at my symmetrical curve, right here in the middle is mu, and let's recall what mu stands for, which is mean. So if the middle is the mean, and each deviation I go out from the mean, remember sigma is standard deviation. So if I take the mean and I add a standard deviation this direction, or I subtract a standard deviation in this direction, I get a range from a small to a large number. And inside that range, what this is saying is 68% of the population data will lie within one standard deviation of the mean. So right here in the middle, this is going to be the standard deviation of one deviation from the mean, and 68% of the population will lie in between there. So all of this data in here is 68% of the total population. Now, if we keep going, we can go on to 95. 95% of the data will lie within two deviations. So if I take my mean and I go out not one, but two deviations this direction, and two deviations this direction in the smaller direction, if I go out two deviations, that is 95%. 95% of my data will lie within two deviations of the mean, everywhere in that green area. Now if I go out three deviations and I go out just one more, three deviations to the right and three deviations to the left, well then that entails 99.7% of the data. So everywhere from here all the way to here, but then it stops. There actually are these two little endpoints that don't quite ever get met. Okay? Theoretically, this normal curve goes on and on and on forever and never quite touches. There's always going to be this vacant space inside. So there is area inside of here. That's why we can never say 100%. We can only go up to 99.7%, which is within three deviations of the mean. If I were to break those deviations down into percentages, this middle 68% can be broken down into 34 and 34%. If I break down the middle 95%, it would break down into 34, 34, plus 13.5 and 13.5, and those four numbers all add up to 95%. If I were to break down the 99.7%, you have this middle 95 plus an additional 2.35 on the ends, which adds up to the 99.7, which means I have 0.15% left over for these tails on the ends in order to equal out to 100% total. So let's look at an example. Let's say we have IQ scores that have this bell-shaped distribution with a mean of 100 and a standard deviation of 15. So let's first label the curve with that data. So my curve is going to have a mean of 100, so that's going to be here in the middle, with a standard deviation of 15. So if I am one deviation smarter than the average, I have an IQ of 115. If I am two deviations smarter than the mean, then I have an IQ of 130, and then 145, and so on. So you can see here is the average IQ, and as we move to the right, your intelligence or IQ goes up. On the other side, we're going to go lower. If you are one deviation less than the mean, your IQ is 85. 2 deviations less would be 70, and 3 deviations less would be 55. So once I've labeled my curve, it'll be much easier to be able to answer these questions. So what percentage of people have an IQ between 70 to 130? Well, here's 70 all the way up to 130. And what is the percent of the curve, the area that's shaded in, that's between those two values? Well, it's everywhere in between here all the way to here, which represents 95% of the data is within those two values. So 95%. So you could either use the 95% rule because they're both 2 deviations from the mean, or you can add up these 4 circles of percentages. What percent of people have an IQ that is less than 70? So I'll do this in green. So less than 70 or greater than 130. So now I'm looking for the green areas. So what percent of my circle up here is either in this tail over here or in this tail up here? Well, there's 2 methods I could use. I could add these 4 numbers, and if I add 0.15, 2.35, 2.35, and 0.15, you're going to come up with 5%. Or, since I knew that the middle from here to here was 95%, and I know that the whole graph is 100, couldn't I just do 100 minus the middle 95%? Well, that's going to give me the outside 2 tails. That's another way of thinking about it. What percent of people have an IQ of greater than just 130? Well, if I want just greater than 130, then I'm only adding these 2 scores on the end, the 2.35 plus the 0.15, which is going to give me 2.5%. What percent of people have an IQ between 100 to 130? So between 100 to 130. So that's from 100 up to 130. And so I want all of this area in between. So all of this area in between, we're going to be adding this number and this number. So it's going to be 34% plus 13.5%. which is going to give me 47.5%. Another way of looking at it is, well, I could do 2 standard deviations below all the way to 2 standard deviations above, which is 95, and then just take half of that. So I could do 95% and then take half, which is also 47.5%. So there's 2 ways of thinking of that question. So moving on to the next page. In section 3.3, it talks about group data. We're actually not going to cover that section. We're going to move right into section 3.4, which talks about Z-scores. Okay? Why we need what's called a Z-score comes from the previous picture. So in these particular questions down here, I asked you specifically if you had an IQ of between 70 and 130, how many people would be in that group. So 70 and 130 happen to lie right on a boundary line, so I was able to tell you exactly how much was underneath the curve. But what if I change those numbers to 75 and 125, for example? And I said, what percentage of people have an IQ between those 2 scores? Well, the unfortunate part is 75 isn't a boundary line. It's somewhere around here. and 125 is somewhere around here. And I said, well, how much data is in between those squiggly black lines? Well, that would be hard to determine because I wouldn't know how to break down this rectangle into two different parts since they have two different heights. So I wouldn't know how much area is in between here because it doesn't lie right on a boundary line. So how do we calculate those probabilities? Well, that's where z-scores come in. What a z-score is by definition is it represents the distance that a data value is from the mean in terms of the number of standard deviations. We find it by subtracting the mean from the data value and dividing this result by the standard deviation. We have one for both population and for sample. We usually use the sample because usually we have that information, and z-score is found by taking the data value minus the average, which is the mean of the sample, divided by the sample standard deviation. The z-score is unitless, so it has a mean of 0 and a standard deviation of 1, and it does not have units. So if I go back again one more time to my picture over here, which is getting a little confusing, let me cover up some information down here. So if I've got my symmetrical table one more time over here, and I have all of my means and my standard deviations. Here's my mean, mean plus 1 standard deviation, mean plus 2, mean plus 3. Over here I have mean minus a deviation, mean minus 2, and mean minus 3. Well, each of those are going to have individual z-scores. In the middle, the z-score is 0. Because remember, the z-score stands for how far away a data point is from the mean. And if the mean is right here in the middle and your data value is in the middle, then your z is 0 because you are 0 away from the mean. Now, if you are exactly one deviation to the right, then you have a z-score of 1, meaning you are one deviation larger than the mean. You could be 2 deviations larger than the mean, 3 deviations larger than the mean. You could even be 4 deviations, 5 deviations, or even 6 deviations larger than the mean. But this becomes quite improbable the farther out we go, because looking at the size of the probability in between is very unlikely. If you are smaller than the mean, then you have a negative z-score. In other words, you are 1 deviation smaller than the mean. You could be 2 deviations smaller than the mean, 3 deviations smaller than the mean, and even smaller, smaller, and yet smaller. But again, that becomes quite unlikely by looking at the probability inside the graph. It would be very unlikely. So going back to our z-scores, let's do an example and find some z-scores in regards to these two individuals. We say that the average 20-year-old man is 69.6 inches tall, which is 5'9½", with a standard deviation of 3 inches, while the average woman is 64.1 inches tall, which is 5'4", with a standard deviation of 3.8. So let's pause for a minute. I'd like you to think about, where do you lie? If you're a man and you are taller than 5'9½", that means you are above average. That means you will have a positive z-score. If you are smaller or shorter than 5'9½", you will have a negative z-score. For a woman, if you are taller than 5'4.1", that means you will have a positive z-score. And if you're shorter than 5'4.1", you will have a negative z-score. If you are exactly one of these numbers, you will have a z-score of 0. Okay, so let's go on to the question which says, who is relatively shorter, Kevin Hart or Snooki? So if I didn't use the word relatively and I simply just said who is shorter, you would answer Snooki, because just looking at the two numbers, clearly she is shorter than Kevin Hart. However, when I say relatively shorter, that means relative to their own gender. So we have to take into consideration that the average is different. So if we look at Kevin, and we look at Kevin's Z-score, we take, by definition, we take his data value. Okay, so he is 5'4". So 5'4" in inches is going to be 60 inches plus 4 more, so he's 64 inches tall. So I would take 64 and I would plug that in for x, and then we subtract the average man. The average man is 69.6 inches tall. This is x bar for a man. So we're going to subtract 69.6 inches tall, and then we divide by the standard deviation of a man. The standard deviation of man is 3 inches. So when I put all of this into my calculator, I get 64 minus 69.6 divided by 3, and this says that Kevin Hart has a z-score of negative 1.86 repeating. Now, if I do Snooki's z-score, I take her data value. She is 4'8". So I'm going to take 48 inches and add another 8. So that brings me to 56 inches tall. I'm going to subtract the average woman, and the average woman is 64.1. And I divide that by the sample standard deviation. The sample standard deviation of a woman is 3.8. And when I put all of that into my calculator, Snooki's z-score is negative 2.13. Approximately. Okay? So if I go back to my curve just for a moment again, if I go back to my curve for just another moment where I had those z-scores, okay? Remember we were just talking about these? And we said that here's your z-score if you're average, and we just decided that Kevin Hart was negative 1.8 z. So Kevin Hart is somewhere between negative 1 and negative 2. He's actually right around here. He has a z-score of negative 1.8. That's Kevin Hart. Snooki has a z-score of negative 2.1. So she's somewhere over here between negative 2 and negative 3. So Snooki is over here but at negative 2.1. Remember, here was the mean. So when the question says who is relatively shorter, the question is asking who is farther away from the mean. In this case, Snooki is farther away from the mean because her z-score is a larger number. I should say the absolute value of it is larger. So it is farther away from 0 or on the number line. So to answer this question, Snooki is relatively shorter. So let's try another one, but this time let's decide who is taller. So I'd like you to think of this question, pause the video, and try this one on your own. Alright, so I went ahead and did the work. I found that Shaq has a z-score of 5.13 repeating. I took his height, which is 7 foot 1 inch, minus the mean divided by standard deviation, and found that he has a z-score of 5.13. That is very far outside of the mean. Candace Parker, who is also a WNBA player, she has a height of 6'4", which is very tall for a woman. She's 76 inches tall, which gives her a z-score of 3.13. So again, if I go back to that picture that I had up here and I look at the z-scores one more time, okay, we see that Shaq has a z-score of 5.13. So 1, 2, 3, 4, 5. So Shaq is way out here with a z-score of 5.13. Candace Parker has a z-score of 3.13, which is somewhere over here. So the question is, who is relatively taller? In other words, who is farther away from the mean of 0? Well, clearly Shaq is farther away because his z-score is a larger number. So to answer this question, Shaq is relatively taller. A person is deemed unusual if they lie outside 2 deviations from the mean. Are any of the above people considered unusual? So remember, unusual is anybody outside 2 deviations, whether it be tall or short. Kevin has a z-score of negative 1.8. He is inside 2 deviations, so he is not unusual. Snooky is unusual. She is outside 2 deviations from the mean. So she is farther away from the mean by more than 2 deviations. So she is unusual. Shaquille O'Neal is unusual. He's more than 2 deviations far from the mean. Candace Parker is unusual. She is farther than 2 deviations away from the mean. All of them are unusual. Who is the most unusual? Shaquille O'Neal will be the most unusual because he has the largest absolute value of a z-score. He is the farthest from the mean. Okay? So at this point, I'd like you to calculate your own z-score now and think about, is anybody in the class unusual? You might not know that information. We can definitely do that when you get back to class, but think about your own z-score. Are you above or below the mean? Are you unusual? And think about that. Now is a good time to pause the video. After you finish there, we're going to move on now to the next page where we talk about percentiles. Percentiles are a way of dividing your data into quarters. So the kth percentile, which is denoted as a capital P, is the set of all data where the value is a kth percent of the observations. For example, if I said explain the meaning of the 95th percentile of test scores, this means that 95% of people score less than the student. Or you could say 5% of people scored better. So breaking the percentiles down into quarters, just like a football game, is what we are going to do here. Okay? In dividing them into quartiles, the first thing you're going to do is arrange your data in ascending order. So the smallest value will be first, which is called your minimum. The largest value will be last, which is called your maximum value. Then we determine what the median is. We call this the second quarter. So the median is always the middle of your data, and it's always going to be the middle value. This is basically halftime of a football game. Then to find quarter one and quarter two, or the ends of the first quarter and the ends of the third quarter, we then divide the first half in half. So just like it's saying to do here, we're going to divide the bottom half of data in half, and that's how you find quarter one. And then if you divide the upper half in half, that's how you find quarter three. The interquartile range is the range of the middle 50%. The middle 50% is found by taking Q1 all the way through Q3. This is what we call your IQR, or your interquartile range. Remember, each of these quarters is 25% of the game, or 25% of your data. So the middle 50% is found by taking the second quarter and the third quarter and adding them together. This would be your IQR. You can also find the range by subtracting the Q3, which is the larger value, minus Q1, which is the smaller value, and then the range of values in between there would be the range of your interquartile range. Note, do not include the median when determining Q1 and Q2 by hand. And we're going to do an example of that in just a moment. How do we know when to use mean or median? If your distribution is symmetric, we will always use mean for symmetric graphs. The bulk of this course is generated from symmetric graphs, so we'll be talking about mean an awful lot. Also, standard deviation, which goes along with mean because we need that in order to determine how the curve looks. However, if your curve is skewed in one direction or the other, we generally like to use median and IQR instead because it is in a skewed direction. So let's do an example on the next page of how to determine whether we have outliers. Outliers are going to be a number that is far outside of your data, okay? So something that looks like it may or may not belong in the data set. The first thing we need to do is determine what the IQR is. So we're going to determine the first and the third quartiles and then find the IQR. And remember, the IQR is found by taking Q3 minus Q1 like we did on the previous page. Then we determine what are called the fences. The fences serve as the cutoff points for determining where the outliers may be. The lower fence is found by taking your first quartile minus 1.5 of your IQR, and then we find our upper fence in the same fashion. If a data value is less than the lower fence or bigger than the upper fence, it's considered an outlier. This will become much easier when you see this in an example down here. So we have the following data, which represents the miles per gallon of a random sample of smart cars with a 3-cylinder 1.0 liter engine. And the sample mean is 38.78 miles per gallon. So this is the sample mean right here. And the sample standard deviation is 3.42, again, miles per gallon. Okay. So out of all of these, how many cars do we have? 1, 2, 3, 4, 1, 2, 3, 4, 5, 6. We have 24 cars. So N is 24. So out of all 24 cars, we have an average miles per gallon of 38.78. Certainly some are smaller and some are even bigger. But on average, we have a miles per gallon of 38.78. We also have a standard deviation. So the first question says, let's first compute the z-score corresponding to the individual who obtained a 36.3 miles per gallon. Okay, so let's first find the z-score of this particular car. So I have a car and I am getting 36.3 miles per gallon. So that's my individual raw data score. So in my Z formula, I take the raw data, which is 36.3. I subtract the average, which is 38.78. In other words, that's how far from the mean I am. I am below average, so that means I'm going to have a negative Z-score. And then I divide that by my standard deviation, which was given to me in the problem. So when I put all this into my calculator, I'm going to get negative 0.72, and you can check that. So it also says to interpret. This is something important. On an exam, you'll see words like interpret. So a lot of students will forget to do this part. This means write a sentence on what you just found. A good sentence would be that this car gets slightly better gas mileage than the average smart car. And the reason I said better is because a negative represents a better gas mileage. I'm thinking about that. I think I have that wrong. I think I should say worse. I should say worse. I apologize for that. Worse gas mileage because they're getting less miles for the same tank than the average car. So if you're getting less miles with a negative z-score, you're getting worse gas mileage. So my apologies, but I'm glad I caught that. Okay, so now in part B, we're going to determine what the quartiles are. The quartiles are going to be these numbers that are in the first, second, and the third quartile. Okay, so let's determine what those quartiles are. So first we need to find the median. So the median I'll put in the middle. So the median is going to be also known as Q2. Once we find that, we can then find Q1, and then we can find Q3. Okay? So once we find the median, we'll be able to find the other two. Luckily, these are all in order. Okay, rather than writing all of these out again, which you certainly can do, they are in order already, starting from the first, and we work down. So this is the smallest, and then we come over here, to here, to here, here, and then this would be my biggest value. Okay, so if I were to imagine all of these written out in a line, I could determine that the median is going to be the middle of this data. The median will be somewhere where there are 12 data points on this side. Working backwards, there are 12 data points on this side. So somewhere in between this value and this value will be the median. So the median will be halfway between these two values. So my median should be somewhere between 38.3 plus 38.4, and we have to divide that by 2. And when I do that, I should be getting 38.35. That's my Q2, or my median. Now I'm going to find my Q1 and my Q3. Okay, so my Q1, if this is my median somewhere in between these two values, then I take the the median of the bottom half. So where is the median of the bottom half of the scores? So again, if I go up 1, 2, 3, 4, 5, 6 data points from the bottom, and then from here I go up 1, 2, 3, 4, 5, 6 from this side, my Q1 is going to be lying right in here. So somewhere between 36.3 and 37.4. So I have to take the average of those two values. And when I take the average, I get 36.85. Over here, if I want to find Q3, again, I take the median of the upper half of the data points. So if I start from the bottom and I count up 1, 2, 3, 4, 5, 6, and then up from the bottom, I count 1, 2, 3, 4, 5, 6. So my median is going to be somewhere in between here, which is in between 40.6 and 41.4. And of course, I have to divide by 2. And when I do that, I get 41.0 for Q3. So I have found quartile 1, median, and quartile 3. So for part C, it then asks me to compute and interpret the IQR. By definition, the IQR is defined as by taking Q3 minus Q1. So I take Q3, which is 41, and I subtract Q1, which is 36.85, and I find the IQR is 4.15 wide. In an interpretation, I would say that the middle 50% of smart cars have a range of 4.15 miles per gallon. So the last question says, are there any outliers? So in order to determine whether there's outliers, I need to determine where the fences are. The fences determines whether there's an outlier. So by the definition, I first have to find what's called the lower fence. The lower fence is found by taking the first quartile and subtracting 1.5 times your IQR. So in this case, it's going to be Q1, which is a 36.85. We subtract 1.5 times my IQR, which is worth 4.15. And when I put that into my calculator, I get a lower fence of 30.625. So when I determine my lower fence, I ask myself, are any of these data points outside of that lower fence? So looking up here, my lower fence is going to be at 30.625. So let me look up in my data set. 30.6, well, there's no data values. My fence is way up here. And there's no data values outside of 30.625. There are no data values out here. So there are no lower outliers. Let's also check for upper outliers. So we need to find the upper fence. So we take Q3 and we add 1.5 times the IQR. So that's going to give me 41 plus 1.5 times 4.15, and that's going to give me 47.225. So if I, again, go back up to my data set and look at the fence of 47.2 miles per gallon, 47.2 would be right in here. 47.2 would be my upper fence, which states 47.5 is an outlier because it is outside of the upper fence. So 47.5 is an outlier. An outlier is determined to be a value that lies far away from the mean. So in the last section, we're going to take all of that information that we just learned and we're going to put it into a graph, which is called the box plot. Okay, the box plot is found by taking the 5-number summary and putting it into a graph. The 5-number summary is the minimum and the maximum value, smallest and biggest, the median, which is the middle, Q1 and Q3. And remember, in a graphical format, you've got all of your data from smallest to biggest. You've got your middle, which is your median. That's halftime of the football game. And then you've got the end of the first quarter and end of the third quarter. So we're basically breaking that number line down into 25% apiece. So we're going to take each of those 5 values and draw a box plot. In order to draw a box plot, you need the lower and the upper fences. You need to know what the IQR is. And then we'll draw this number line that is long enough that includes both the minimum and the maximum. We'll insert vertical lines at each of the quarters, similar to what I just did up here. Then we'll enclose these vertical lines in a box. So between Q1 and Q3, we'll actually enclose these in a box because this is what is actually your IQR. We'll then draw a line from Q1 to the smallest data point, which is what we did here. Draw a line from Q3 to the largest data point, which is what we did here. And then we'll also draw in the upper and lower fences, okay? Any data values that are less than the lower fence, we will designate those as an asterisk, as an outlier. So let's show some examples of what these look like here. Let's look at the symmetrical curve first. If we look at the symmetrical curve, you can see that it has a box plot that is very even on both sides because it's symmetrical. So it has a median in the middle, a Q1 and a Q3 that are approximately equidistant from the median, and both of these whiskers are about the same length. However, if you have a graph that is skewed to the right, you're going to have a box that is on the left side of the graph because that's where the bulk of your data is. So your median will also be on the left. So you're going to have a larger third quarter and an even larger fourth quarter. So Q1 and Q2 are going to be relatively small in size. On the other side, if we have a skewed left graph, most of your data is on the right-hand side. So it's going to appear that your whisker to the right and your third quarter are actually small in size because you have a lot of data points in there. But then you have a large second quarter and even larger whisker to the left because of that outlier that might exist. It's pulling everything to the left. So let's go ahead and do the box plot of the previous smart car example. Let's do one by hand and then we'll do one in StatCrunch. So in order to do a box plot, the first thing we need to do is make a number line. So from the previous example, we know that we had data that ranged as low as 30 up to, let's go all the way up to 50. So let's just make a number line from 30 all the way up to 50. And then let's put some data values in there. So 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. Okay. So then once we have a number line, we're going to put our minimum, maximum, and quarters values in there. We know that we have a minimum value. The smallest value is at 31.5. So the smallest value was here at 31.5, which is our minimum. Our maximum value is 47.5, which is right here. So that's our min and our max. We also know that we have a lower fence at 30.6. So at 30.6, which is right here, fences are drawn as brackets. We have an upper fence at 47.2, which is right here, which is drawn as a bracket. Okay. Then what we do is we draw our lines. So we're going to draw a line from the where the first quarter and median and third quarter goes. We have Q1 was equal to 36.85. So 36.85, this is Q1. The median was located at 38.35. And Q3 was located at 41. So this box represents the IQR. This box is my IQR in here. Interquartile range. Then what we do is we draw the whiskers from the outside of the box to the smallest data point and to the largest data point that is within your fence. This guy is outside of my fence. So this data point is actually going to get an asterisk representing that it is an outlier outside of my fence. So the next data point inside my fence, the next one lower, will be 43.5. And I'm going to draw my whisker to that data point there. So this would be an example of what the box plot would look like for the above information. I'm also going to do this in StatCrunch. So let me turn that around. Okay, so I went ahead and entered all of the data from the smart car example into StatCrunch. You can see into the first variable here. I could even go as far as to rename the variable miles per gallon. Okay, so once I've done that, according to the instructions, I'm going to draw a box plot by going into graph, and then, graph, and then clicking on box plot right here. So let's put all of the information into the box plot that I need. First, it asks me to select the column for which I want to create the box plot, obviously miles per gallon. I'm not going to change anything else. I'm going to go ahead, let's go ahead and put the mean and median on the graph just to see what it looks like. We're also going to click on use fences to identify outliers. And I'm going to draw the boxes horizontally. I think by default it does them vertically, but the book and the notes all draw them horizontally. So I'm going to go ahead and draw them horizontally. And I'm not going to change anything else. So let's go ahead and compute this. Let's see what it looks like. Okay, so there's my box plot. It's similar to what we drew as you can see on the page. You can see that we have our number line down here at the bottom, which is the same number line that they have down here from 30 up to 50. You can see that they have the vertical lines here are your fences. So this is the lower fence, which we have here. We have an upper fence over here, which is at 47. And we have an outlier. And there's our outlier, which is right there. We have the box inside. The green stands for the median, so that's what this line is right here. It also plotted the mean inside. And since the mean and the median are not identical or close, this is maybe slightly skewed. Since the mean, and if you hover over these, you can see that the mean and the median of these two values are slightly different. So since the mean is 38, and we can click on it, find the median here. Median is also 38. Oh, so they're pretty close. So it's maybe fairly symmetric, maybe slightly skewed. But the box inside, this is your interquartile range, which we have here. And that's it.